Distinguished scholars, ladies and gentlemen, my name is Jiang Bian from China University of Petroleum. It's a great honor to have this opportunity to give a speech at this conference. Today my topic is treatment of natural gas with varying CO2 concentration using supersonic flows. My presentation will be divided into the following parts. As we all know, most of the natural gas contains excess CO2. The existence of CO2 can cause serious corrosion to equipment and pipeline, reduce the heating value of natural gas, and even cause serious environmental problems. Therefore, it is necessary to separate the CO2 from the natural gas. And the supersonic separator is a new device for natural gas processing. It has a small size and flexible structure, which makes it more suited for unmanned operations such as the gas-fired in the offshore, desert, and remote areas. As shown in this figure, natural gas expands to supersonic in the nozzle, resulting in low temperature and pressure. Nucleation and condensation of CO2 occurs, followed by the growth of liquid droplets. Then the liquid droplets are centrifuged onto the walls and removed from the dry gas. And the nozzle is the most significant part of the supersonic separators. Some scientific research has focused on the condensation characteristics of supersonic gas in the nozzle. In our previous research, we have also conducted some studies on the condensation of water vapor and the liquefaction of natural gas in the nozzle. So in this paper, in order to review the supersonic condensation characteristics of CO2 in natural gas, we established the mathematical models and numerical schemes for the CH4-CO2 mixture gas and studied the influence of inlet CO2 concentration on the CO2 removal efficiency. The Gaussian equations for the mixture, including the equation of mass, momentum, and energy, the droplet number density equation, and the relation between the droplet readings, droplet number, and liquefaction rate are employed to describe the liquid phase. And in the above equations, the internally consistent classic theory was adopted to calculate the nucleation rate, and the geometry model was employed to calculate the growth rate of droplets. The K-omega turbulence model was used to predict the supersonic flows in the nozzle. The inlet and outlet boundary are set respectively according to the flow characteristics of the supersonic compressible gas, and the nozzle wall is set to be no slip, no seepage, and adiabatic. The nozzle mainly includes three parts: subsonic section, critical section, and supersonic section. The length and diameter of each section are shown in this table. And the experimental data of MOSES are adopted to verify the mathematical models and numerical schemes. As we can see in this figure, simulation results obtained is in good agreement with the experimental values. Most of all, the position of the spontaneous condensation is accurately captured by the simulation, which shows that the models and methods used in the simulation are feasible. The numerical methods established above were used to simulate the condensation process of CH4CO2 mixture gas. The calculation conditions are as follows. We obtained the key parameters of CO2, including the nucleation rate, droplet number, droplet readings, liquefaction rate, and the concentration of CO2 gas. These two figures are the nucleation rate and droplet number distributions with different gas composition. As we can see, the nucleation rate of CO2 sharply increases in a very short distance. After that, due to the sharp fall of the subcooling, the nucleation rate dropped from the peak to 0, and the nucleation process completed. With the increase of the inlet CO2 concentration, the nucleation position is advanced and the maximum nucleation rate and droplet number decrease obviously. This is because with the increase of the inlet CO2 fraction, the particle pressure of CO2 is bigger and the condensation is more likely to occur. And the distributions of the droplet readings and liquefaction rate of CO2 are presented in these two figures. As seen, when the condensation occurs, droplet readings and liquefaction rate increase rapidly in the early stage. This is because after the nucleation rate reaches to the peak, a large number of vapor molecules will grow on the surface of the droplets, which makes the droplet readings and liquefaction rate increase rapidly. After this stage, the readings and liquefaction rates increase slowly, reaching the maximum value at the outlet of nozzle. In addition, the droplet readings and liquefaction rate increase with the increase of inlet CO2 concentration. And this figure shows the concentration distribution of CO2 in gas phase. It can be seen that the concentration of CO2 is higher with the higher inlet CO2 concentration, even though the readings of droplets is larger and liquefaction rate is higher. More CO2 remains in the gas phase. When the inlet CO2 mole fraction is less than 10%, the CO2 fraction in gas phase is almost 0, which indicates that the low temperature separation technology is feasible for the treatment of natural gas with low CO2 concentration. And these are the main conclusion of this paper. Okay, that's the end of my presentation, and thank you very much for your kind attention. And you can also email me if you have any questions. That's all. Thank you.